the largest, most powerful, and most complex space telescope ever built, begins its journey into space.
In a groundbreaking revelation, the James Webb Space Telescope challenges long-standing notions about the Big Bang. Since the discovery of the cosmic microwave background in the mid-20th century, we've refined our understanding of the universe's age and composition. While prior observatories like Hubble hinted at cosmic evolution, James Webb's unparalleled capabilities allow us to witness, for the first time, the complex details of the universe's growth on stellar, galactic, and supergalactic scales. Join us as we reveal groundbreaking findings from the James Webb Telescope challenging the Big Bang theory, the evolution of our cosmic perspective. Only 100 years ago, in 1923, Edwin Hubble made a groundbreaking discovery that changed our understanding of the universe. While observing the Great Nebula in Andromeda, he realized that a periodic light he initially thought was a nova was a variable star much farther away than any in the Milky Way. This revelation provided the first clear evidence that spiral and elliptical nebula, once thought to be part of the Milky Way, were separate galaxies, referred to as island universes at that time. Today, we know the observable universe contains trillions of galaxies, with some dating back to when the universe was less than 3% of its current age. Although we can only see stars and nebula within our Milky Way and a few nearby galaxies, observatories like Sloan Digital Sky Survey, Hubble, and James Webb enable us to explore the universe in both its near and distant aspects. While we've mapped only a small fraction of existing galaxies, three-dimensional reconstructions show their diverse shapes, sizes, and groupings. Galaxies exhibit variations like giant ellipticals in rich clusters and familiar spiral shapes on the outskirts, or in isolated regions called fields. To understand the universe's past, we delve deeper. Initially, the universe differed significantly from its present state: dense, expanding faster, less clumpy, and hotter. Today's cosmic expansion is linked to the energy density of space, a concept not applicable to the early universe. Comparative galaxy studies, examining galaxies from different epochs, reveal significant evolution over billions of years. Pencil beam studies, observing tiny regions devoid of nearby stars or galaxies, help uncover distant galaxies using infrared light. Hubble's Deep Field View, before James Webb, revealed over 5,000 galaxies, spanning from nearby to over 13 billion years ago. However, limitations persist. We likely observe only a small percentage of existing galaxies, biased toward large, bright ones. Satellite galaxies, common but faint, often escape detection. The universe's first 550 million years, shrouded in light-blocking neutral matter, remain largely unseen. Moreover, actively forming starburst galaxies triggered by major mergers present challenges in observation. Despite advancements, these observations illuminate only a fraction of the cosmic fabric. James Webb's quest for early universe secrets. NASA's James Webb Space Telescope has been specifically designed to overcome limitations, including those of the Hubble telescope. It observes the universe using larger eyes optimized for infrared wavelengths and the ability to penetrate light-blocking neutral matter. Unlike Hubble, James Webb has discovered many galaxies that exceed the limits of previous observations, such as the JDS series, Glass Panoramic Cosmos Web, and more. These observations provide unprecedented insights into the early universe, challenging previous assumptions about galaxy growth. The telescope has shattered several cosmic records, allowing us to visualize the young universe in ways never before possible. The sheer number of galaxies found in the early universe exceeds predictions, prompting questions about the formation of stars and galaxies. The data collected by James Webb, particularly from the James Webb Space Telescope Advanced Deep Extragalactic Survey Field, revealed a record holder with a confirmed redshift of 13.2, corresponding to an age of just 320 million years after the Big Bang. Despite the unexpected discoveries, the current record is expected to be surpassed with more extensive and deeper data collection. James Webb's comprehensive survey of 100 square arc minutes, in collaboration with Sears Collaboration, has unveiled a multitude of galaxies, challenging theoretical models of galaxy formation. The telescope's findings suggest a lack of understanding in current models, leading to questions about early galaxy brightness, mass, and star formation. The high number of early galaxies detected implies a gap in our understanding of galaxy formation and its evolution over billions of years. Possible explanations include factors like dark matter or unconsidered forces influencing early galaxy formation. As James Webb continues to gather data, it promises to provide more answers to existing questions and unveil new mysteries, bringing us closer to a comprehensive understanding of the universe from its earliest moments to the present day. The discovery of the most distant galaxies is just the beginning, and as James Webb collects more data, our grasp of the universe becomes increasingly achievable. New Horizons with James Webb. Recently, James Webb surprised the world with a new, high-definition view of an exploded star. The image reveals the supernova remnant known as Cassiopeia A in a fresh light. Located light years away in the Cassiopeia constellation, this stellar explosion occurred approximately 340 years ago from our perspective. James Webb's near-infrared camera provides a detailed look at Cass A, showcasing intricate details of the expanding shell formed by material colliding with the gas shed by the star before its explosion. Cass A is one of the most extensively studied supernova remnants, observed by various ground-based and space-based observatories, including NASA's Chandra X-ray Observatory, Hubble Space Telescope, and retired Spitzer Space Telescope. In April last year, a new chapter in the study of Cass A began with Webb's mid-infrared instrument, revealing unexpected features within the inner shell of the supernova remnant. Some of these features are not visible in the NIR-CAM image, prompting astronomers to investigate why infrared light is not visible to the naked eye. Webb's latest image of Cass A may seem less colorful than previous images, but this is due to the wavelengths at which the object emits light. The image highlights clumps in bright orange and light pink, representing the inner shell of the supernova remnant. Webb's high-resolution view allows the detection of tiny gas knots composed of sulfur, oxygen, argon, and neon from the star. Embedded within this gas are dust and molecules, eventually becoming components of new stars and planetary systems. Cracking the nebular code. James Webb has once again focused on a supernova. Just a few months ago, it observed the Crab Nebula, a leftover from a supernova explosion that happened 6,500 light-years away in the Taurus constellation. Since ancient astronomers noted this event in 1054 CE, the Crab Nebula has kept scientists intrigued. Using Webb's NCAM and MIRI, a team from Princeton University, led by T. Tamim, is exploring the origins of the Crab Nebula. At first glance, the Crab Nebula's shape looks like the image captured by NASA's Hubble Space Telescope in 2005. However, in Webb's infrared observation, a cage-like structure of gaseous filaments appears in red-orange. In the central regions, emission from dust grains is mapped in yellow, white, and green for the first time. This reveals more details about the inner workings of the Crab Nebula. Webb's observations highlight synchrotron radiation, emitted by charged particles moving around magnetic field lines at high speeds. This radiation, seen in milky smoke-like material, is produced by the pulsar, a rapidly rotating neutron star at the heart of the nebula. Webb's NIRCam instrument allows astronomers to trace the pulsar's location and observe circular ripple-like patterns, wisps, and radiation ribbons. The curvy wisps, closely grouped, reveal the structure of the pulsar's magnetic field, shaping the nebula. At the center left and right, material curves sharply inward, possibly due to the confinement of the supernova wind's expansion by a belt of dense gas. The pulsar's wind continues to push the shell of gas and dust outward rapidly. Inside the remnants, large-scale loop-like structures made of yellow, white, and green filaments represent areas where dust grains reside. Astronomers are actively seeking answers about the Crab Nebula's past by analyzing Webb's data and consulting previous observations. New Hubble data, after over 20 years, will further aid in comparing findings from Webb and Hubble, offering a more accurate understanding of the Crab Nebula. Weighty questions in the sky. The Crab Nebula has long puzzled astronomers due to a discrepancy in its mass and the observed outcomes of stellar evolution. Generally, a star's initial mass determines its fate, with lower mass stars becoming white dwarfs, and higher mass stars experiencing core collapse supernovae, leading to neutron stars or black holes. However, the Crab Nebula's mass, estimated between 2 and 5 solar masses, doesn't align with the observed core collapse supernova and neutron star. The central pulsar of the Crab Nebula, a neutron star, has a mass of only 1.4 solar masses. Despite uncertainties, even the high mass estimate for the nebula falls short of explaining the observed phenomena. This discrepancy prompts questions about potential flaws in our understanding. Various possibilities are considered, including errors in modeling the nebula, inaccuracies in measuring the neutron star's mass, or the existence of ejected material not accounted for. However, none of these explanations fully resolve the puzzle. The upcoming James Webb Space Telescope promises to provide valuable insights, especially with its ability to map the dust distribution within the nebula in unprecedented detail. The JWST's infrared imaging reveals dust-dominated filaments rich in material, challenging previous observations that may have overlooked dust. Synchrotron radiation, generated by fast-moving electrons in a magnetic field, adds complexity to the interpretation. The presence of dense gas belts and heavier elements suggests potential sources of undetected massive material. The heart of the nebula, where the pulsar is located, displays intriguing features in the magnetic field lines traced by smoke-like wisps. An asymmetry in filament lengths around the pulsar hints at its motion, contributing to the overall complexity. With Hubble set to revisit the Crab Nebula, simultaneous data from both Hubble and JWST could provide a more comprehensive understanding. The hope is that superior data from these observatories will not only reveal detailed structures within the nebula, but also offer a more satisfactory explanation for the mass puzzle, shedding light on the intricate processes at play in this celestial phenomenon. Thank you for watching. See you in the next update.